Good afternoon, everyone. My name is Sophie, and I'm here today with my colleagues from Metis, Claudia, and Charles-Olivier to present to you our design for the Innovation Challenge. The design we're going to present today is the Electromyography-controlled upper limb exoskeleton for patients living with muscular dystrophy. So the presentation will go over the project background, the prototype overview, the unique innovations of our design, the potential markets, and the next steps for our device. Let's start with the project background. Metis is a technical committee of 25 engineering students. Our members come from all kinds of engineering programs, including biomedical, electrical, mechanical, software, computer, and more. We are affiliated with Polytechnic University here in Montreal. Our mission is to promote technological and social innovation in biomedical engineering through our various projects and learning opportunities. The targeted problem for our design is that there is still no known widespread curative treatment for patients with muscular dystrophy. The goal of our project is to create a design that's accessible and customizable, which is to become a tool to improve patient quality of life and give back independence in everyday tasks.
Now we'll continue with the prototype. Our prototype is based on the EMG signal of the patient that we will acquire and process to use for the intention of motion of the exoskeleton that will be determined by an AI model. After, we will use a PDA motor control to move the exoskeleton. And one of the perks of our exoskeleton is that it's fully customizable to the size of the patient. Small or big, no problem. And lastly, for now, our focus is to optimize the hand-to-mouth motion to give them a lot of liberty and autonomy in their daily life. Our unique innovation is the real-time control of the patient on the exoskeleton. It is based on the prediction of movement by our AI model. The AI model that we use is a convolutional neural network that will predict the intention of movement. This model has an accuracy of 99%. So the movement that the patient wants to do, he will be capable of doing it. But another innovation is the exoskeleton for data acquisition that we created. That is replicate the real exoskeleton that we produce, and that will allow us to record the data that we'll use to train our neural network and predict the movement of the patient.
As mentioned before, the exoskeleton is used to help people who have a muscular dystrophy. We know that 250,000 individuals suffer from muscular dystrophy in the US, and 50,000 individuals suffer from neuromuscular disorders in Canada. Also, we mentioned before that there's no curative treatment actually for this kind of illness. So our exoskeleton will help patients maintain their autonomy and regain some kind of quality of life by regaining their mobility. Also, since the AI is fully customizable to the patient, we can extend the technology to other disorders or other illness that restricts the range of motion of the patients. In order to reach that goal, we first have to implement the real-time AI to the exoskeleton using a centralized computer. We also have to optimize the biomechanical properties of the exoskeleton to reach a multiple range of motions and to do multiple movements, since the actual design is used to do only hand-to-mouth motions. We also have to implement safety mechanism to make sure that the articulations of the patient are safe during while doing some dangerous movements for the articulations. We also have to do clinical trials to test those mechanisms and make sure that everything works accordingly. And finally, we can do new features to expand the technology to other articulation and other parts of the body and have a more complete exoskeleton. Thank you for your time, and we will now gladly answer your questions.